Hello everyone, welcome to lecture series on the course Calculus of One Variable. This is lecture 16 and in this lecture we will discuss the notion of monotone sequence. Before getting into the topic, let's recall the term bounded sequence which we have defined in one of the previous lectures. So a sequence xn of real number is said to be bounded if there exists a positive real number such that mod of xn is less than or equal to c for each n belongs to n. Now basically when I say that the given sequence of a real number is bounded, it means that the image set of this given function is bounded. So that is, if xn is a function f from n to r is bounded, means the image set of f, the image set of this function, we consider it as a function from n to r. So the image set of, if xn is this function f from n to r, then image set of f, that is f of x for each x in the domain, but here the domain is a set of natural number, so I can say that f of n for each n in n, which is same as saying f of n by the definition of the sequence is nothing but xn, each term x1 x2 x3, this represents the image of the function f. So this set is same as writing set of all the terms in the sequence xn and belongs to n is bounded. So that is, this set is bounded above and bounded below. So whenever I talk about the boundedness of the sequence, I say that this set, the set of all the terms of the sequence, is bounded above as well as bounded below. Most of the time I use the term the given sequence is bounded above, which means that this image set is bounded above. Also I use the term the given sequence xn is bounded below, which means that this set of the terms of the sequence is bounded below. Why I call this as the terms of the sequence? Because it contains all the terms of the sequence, the first term, second term, third term, and it goes on. So now let us get into the topic monotone sequence. While discussing the graph of the sequence, or while discussing the nature of the sequence, we have come across the sequence which either keep on increasing or either keep on decreasing. So it follows one natural trend. So that is, as you keep on increasing the values of n, the sequence either keep on increasing like this, or it might be keep on decreasing. So that is, so the first value would be this, then this, then this, then this, then this. Okay, so this kind of sequence are called as the monotone sequence. So which when you increase the value of n, it either goes towards either it moves upward or it moves downward. Okay, now we see this first kind of graph, and then I will talk about the second kind of graph later. So these are the terms, this is x1 x2 x3 x4 x5 and it goes on. Okay, now it may not go to infinity, it may, you know, after certain stage it may become a constant sequence, that also is possible. But what one need to verify is that in this kind of sequence, this kind of sequence is called as an increasing sequence, and what one need to verify is that if you see the any subsequent term in this sequence, for example, if this is my xn and this is my xn plus 1, then this xn will be less than or equal to xn plus 1. It's going to be strictly if I use the term strictly increasing. So that comes that we will define later. First we see that increasing. If this xn is less than or equal to this xn plus 1 for each n, then we say that this given function is increasing, and that's true. If I see x1 and x2, in this case x1 lies over here x2 lies over here. So x1 is less than or equal to x2. In fact, it is strictly in this case, even if it can be equal also. x3, again x2 and x3, if you see, then x2 is less than or equal to x3, and this goes on. So this kind of sequence is called as an increasing sequence. On the contrary, if you see this sequence, as you keep on increasing the value of n, the values, the terms of the sequence on this y-axis, as you plot the graph, you see that it keeps on decreasing. Now if I compare the first term with the second term over here, this is my x1, or I mean the point would be 1 comma x1, okay, but in general I call it as x1, which is placed over here, and this would be x2, this would be x3, this would be x4, this is almost same as this x4, I would call it as x5 itself, or maybe x3 and x4 are equal, not an issue at all. Okay, so now what you observe is that if you see the subsequent terms, any subsequent term is you will see that xn, suppose this is my xn and this is my xn plus 1, this is n and n plus 1. If n is the first natural number, the next natural number is n plus 1. That's how we compare, or n minus 1 into n. So what you see is that xn plus 1 is less than or equal to xn. You just see this. In this case, x2 is less than or equal to x3. x3 is less than or equal to x2. x2 is less than or equal to x1. Okay, so what happens is that you see that x1 is the maximum term, and so as you keep on increasing the value of n, this values of xn keeps on decreasing. So this kind of sequence is called as the decreasing. So this is the graphical behavior of the increasing or the decreasing sequence. Now from this graphical behavior, one cannot conclude that the given sequence, I mean the increasing or decreasing sequence are divergent. That's not true at all. Although there are some standard examples of increasing sequence which are xn is equal to n or n square, or here xn is equal to 1 by n, you can see that this sequence is converging to 0. This is although one example wherein it diverges to infinity, but there are some sequences which are increasing but still they are convergent. So we will see those kinds of result here in this session too. Before that, I want to define these terms which we have defined, which we have seen, that's increasing sequence and the decreasing sequence. So the definition of increasing sequence so we say a sequence xn of real numbers is increasing. So the definition of increasing, if for each n we have xn is less than or equal to xn plus 1. So if you put n equal to 1, you will have x1 less than or equal to x2. If you put n equal to 2, you will get x2 less than or equal to x3, and it goes on. Okay, so that is here you will have x1 less than or equal to x2, which will be less than or equal to x3, which will be less than or equal to x4, which will be less than or equal to x5 and x5, and this goes on, right? So now you can see, I mean, if you just consider the set of elements in the range of this sequence, those are going to be simply the terms of xn. You see that this sequence is bounded below, or the image set of this sequence is bounded below by x1. It is bounded below by x1. We don't know whether in this case it is bounded above or not, but for sure it is bounded below. So therefore we can conclude that increasing sequence are always bounded below by the first term of the sequence, by x1. Okay, so that's first note one can make over here. So I write it as clearly any increasing sequence is bounded below by x1. So hence one can say that the given sequence is bounded if and only if it is bounded above, right? So hence, so again I want to make clear that I use the term bounded below. Sequence is bounded below, which is equivalently same as saying that the image set of the sequence is bounded below, because I cannot call the sequence is bounded below since we have not defined that term. So hence such sequence is bounded if and only if it is bounded above. So if you want to check whether the increasing sequence is bounded, then you just need to show that it has an upper bound, because it's already have an lower bound. Okay, now so that's a definition of increasing sequence. I haven't used the word strictly increasing. So even if the sequence is constant, that can be called as the increasing sequence, because the first term would be same as the second term, which would be same as the third term, and it goes on. So in fact that is an example which is bounded, a sequence which is bounded above as well. It's increasing as well as bounded above, right? So because of that equality, this is less than equality, even the constant sequence is bounded, is an increasing sequence. Okay, now what we do is that I just remove that equality. So so if I compare any two terms of the sequence, if there is a strictly inequality in any two terms, and in that case the given sequence we call as, that's a particular case we call as a strictly increasing sequence. So that's a particular term kind of sequence we define. We say that xn is increasing, is strictly increasing if xn is strictly greater than xn plus 1 for each n in n. So that is, we have like this: x1 is strictly greater than x2, is strictly greater than x3, strictly greater than x4, and this goes on. So a constant sequence won't fall in this category, and therefore it's not a strictly increasing, although it's a increasing sequence. Okay, now the very analogous term that we defined in this context is decreasing sequence. So we see the definition of decreasing sequence. So it is just similar to what we have defined in the above definition. Instead of increasing, you will have a decreasing. So we say a sequence xn of real number is decreasing definition of decreasing if for each n in n we have, okay, so what we observe is that xn will be greater than or equal to xn plus 1. Just look at this: x1 is greater than or equal to x2, which is greater than or equal to x3, and it goes on. Okay, so this is happening for each n. So we have written here for each n. So that is, In this case, what will be true is that if I put n equal to 1, you will see that x1 is less than is greater than or equal to x2. Okay, and x2 will be, if I put n equal to 2, you will see that x2 is greater than or equal to x3. Then again x3 will be greater than or equal to x4, and this goes on. So it's exactly the reverse way, and so you can see that this sequence is in fact bounded above, bounded from the upper side, because here you see that if I go in this direction, if I start writing from here, x4 is less than or equal to x3, which is less than or equal to x2, which is less than or equal to x1, and so in fact here this is x5, and this side it goes on. So in fact you see that every term of the sequence would be definitely less than or equal to this x1. That is the first term, and first term here in this case serve as the upper bound of this given sequence. So therefore this sequence, such a sequence are always bounded above by the first term of the sequence, and they are going to be bounded if and only if they are bounded from the lower side. So if and only if they are bounded below. So how do we write? So clearly any decreasing sequence is bounded above by x1. Hence such sequence, one can conclude that such sequence is bounded if and only if, again here I am considering the image set of the sequence, is bounded if and only if it is bounded below, that is its image set of the given sequence is bounded below, if and only if it is bounded below. Okay, so we define now again here constant sequence is a decreasing sequence because each terms are equal over here. So in fact the constant sequence is an example which is increasing sequence as well as the bound which is a decreasing sequence. Okay, but if I construct a definition of strictly decreasing sequence, then in that case that the constant sequence is not strictly decreasing. So we define in a similar way a strictly decreasing sequence. We say that sequence xn is strictly decreasing if xn is strictly greater than xn plus 1 for each n in n. So each term x1 would be strictly greater than x2 and x2 will be strictly greater than x3, and this goes on. So there is no possibility of equality. So in fact a sequence which is strictly decreasing, one can conclude that it is increasing, but decreasing, but if it is decreasing then one cannot conclude that it is strictly decreasing. Like an example of a sequence, a constant sequence, it is decreasing but it is not strictly decreasing. Similarly in the above terms where we have defined, as I already said, that strictly increasing is the particular case of the definition. So if it is a strictly increasing, then definitely it has to be increasing, but increasing do not imply that it is the sequence have to be strictly increasing. Example is again a constant sequence. Okay, now so if the sequence is either increasing or decreasing, then we call it as monotone sequence. monotone sequence. A sequence xn is said to be monotone if it is either increasing or decreasing. Now, so one can conclude that the given sequence is monotone if it is either increasing or decreasing. It can be both, as we have seen one example, a constant sequence which is increasing as well as decreasing. Here are some examples. I would state some example of increasing and monotone sequence. Sequence xn is equal to n. This is monotone because it is increasing sequence. Then xn is equal to n square. This is again increasing. If I consider xn to be equal to 1 by n, this is decreasing. Then if I consider xn to be equal to 2 raised to n, this is increasing. Again, if I consider xn equal to 1 by 2 raised to n, this is decreasing. Okay. Now there are certain sequence which is neither increasing nor decreasing, and that's why they are not monotone sequence. All these examples are of monotone sequence. So there are certain sequences which are, like for example, xn is equal to minus 1 the whole raised to n. This is not increasing because it do not satisfy the definition of increasing sequence, nor it is decreasing because again it do not satisfy the definition of decreasing sequence. So why it is not increasing? If you are able to find a natural number wherein n is greater than n plus 1, but xn is not greater than or equal to xn plus 1. Similarly, if you are able to find a natural number n1 wherein n1 is greater than n1 plus 1, but xn1 is strictly not strictly less than or equal to xn1 plus 1. Okay, so if this two choice of natural number you can find, then definitely it's not going to be a increasing or decreasing function. If you see the graph of this function, you see that it varies like this. Okay, so it is not either going towards the top, nor it is coming down, and in fact it is simply jumping from one point to another, and that's why this is not an monotone sequence. One can very easily prove with this idea. Okay, so let's get into the theoretical part. Now the major question that we have, are monotone sequence convergent? Okay, are monotone sequence convergent? So basically, if one think about an increasing sequence, let me first consider only an increasing sequence. So it goes like this, right? Geometrically it moves on like this. Okay, now when one can say that it would converge to a certain fixed limit? So if I can find a point on the y-axis such that at that point itself it gets accumulate, or it do not move beyond that point, then I can say that this given sequence after certain stage eventually get accumulated near this point. Okay, that's actually same as saying, if I can find a bound for this sequence, upper bound for this sequence, such that it do not cross that line, so then in that case I can find a limit for that sequence, or I can find a point where the sequence get accumulated. So that's nothing but the least upper bound of the range of the set in that case. Okay, so that's the idea, and the similar idea is applicable for the sequence which is decreasing. So it keeps on moving, right? If it tends to minus infinity, then definitely it's not going to be bounded, and it's not going to be a convergent sequence. But if I can find a point after which the sequence stopped exceeding, that means from this line onward the sequence is not crossing this line. So that means we should be able to find a point wherein the sequence get accumulated. Okay, and that's nothing but the infimum of the range of the sequence. So we will prove the result for an increasing sequence, and an analogous statement will be framing for the decreasing sequence, which one can prove very easily using the same idea. So that's the theorem we have. These theorems are called as the monotone convergence theorem in a monotone sequence. So it is convergent if and only if it is bounded. So a sequence, monotone convergence theorem says that a sequence is convergent if and only if it is bounded. So we will split the result for the increasing sequence and decreasing sequence, because if it is monotone, then it will be either increasing or decreasing. So we need to know how to produce a result for both. So let me call this as a theorem. In fact, it's 11th theorem, not 11th theorem, I'm not sure. 9th theorem, 2.9. Let xn be an increasing sequence. Then it is convergent if and only if it is bounded, and it is bounded only when it's an increasing sequence. So it is bounded only when it is bounded above. So then it is convergent if and only if it is bounded above. Okay, so okay, if I use the term bounded, then it has to be by the definition bounded above, because every increasing sequence is always bounded below. So only thing we need to show that it is bounded above. Now the proof for this is the idea which we have mentioned above. So first I would take the direct implication. That's very simple to show. Given sequence, let xn be increasing. In fact, that's a common statement, and convergent. Okay, so once you know that it is convergent, immediately you can say that it is bounded. So in fact, in this case we are not even using the fact that it is an increasing sequence. So since xn is convergent, it is bounded, and therefore it is bounded above also. So that's the first part. Now if we see conversely, so conversely I assume that the given sequence is increasing and bounded above. So let xn be increasing and bounded above. So the idea is clear. We are going to just consider the image set of this sequence, and I am going to show that it has a least upper bound by using order completeness of R or LUB property. So consider let me call that image set as R, the range xn image set of xn. Okay, so what we want to show is that the given sequence is convergent. So I'll get to that part. So yeah, so we will have to start with an, okay, I'll go to that part later. So first I will show that this sequence has a least upper bound by using LUB property. So what are the hypotheses that are required is that this, you show that this set is non-empty and you show that this set is bounded above, and it is clear, it is already mentioned that the given set is bounded, so it is bounded above, and R is non-empty because you can find at least one element x1 in this set. Okay, so clearly R is non-empty and bounded above, as the reason for this is that it's already given that xn is bounded, or in fact bounded above. Okay, because it's increasing sequence, you don't have to talk about bounded below, it's always bounded below by the term x1. Okay, so only thing when so that means when I want to say that it's bounded, that means it's bounded above. Okay, so given sequence is always bounded below, that will be always true because it's an increasing sequence. So therefore these are the hypotheses that are required to use the LUB property or the order completeness. So by LUB property, what happens is that there exists an element in R which acts as the supremum for this set, okay, such that supremum of R is the whole set L, I mean the whole number is the number L. Now see, from what we have seen above in the diagram, as I mentioned, it should get accumulated at certain point, and that point is nothing but the least upper bound, because if it's getting accumulated at this point, then definitely the point which lie above that is forms an upper bounds. So there will be infinitely upper bounds, but at certain fixed stage this sequence has to get accumulated, and that's nothing but the least upper bound, and after that stage the sequence will stop crossing, so that acts as the boundary for the sequence. So therefore we claim that this is the required limit of the given sequence. So we claim that xn converges to L. Okay, so I'll start with any epsilon positive. Let epsilon positive be given. So using the definition of the conversion of sequence, we prove that the given sequence converges to L. So okay, first I use the fact that this L is the supremum of R. So since epsilon positive is any given real number, what will happen is that L minus epsilon is not an upper bound of this R, right? Because L minus epsilon is less than this L, and L is the least upper bound. So this implies that, so I use the fact that L minus epsilon is not an upper bound of R. So what does this say? That means we should be able to find at least one element in R which is greater than this L minus epsilon, right? So that's as same as saying there exists at least one natural number, say n, such that for that corresponding to that natural number xn is greater than this L. Okay, so instead of saying that there is an element in R, because R is nothing but set of all the collection of elements of xn, where n is a natural number. So this is same as saying therefore there exists n in n says that L minus or xn is greater than L minus epsilon. L minus epsilon is not an upper bound. Okay, now you can observe one thing. So let me call this as 1, or this should be capital N. I'm sorry for that. This should be capital N. Okay, so now you observe one thing. Whenever n is greater than this capital N, what will happen? Xn will be greater than or equal to xn. The reason is simple. Why? As xn is increasing sequence. Okay. So therefore xn small n will be greater than or equal to x, this capital N, which is greater than L minus epsilon. So, and this is true for all n greater than or equal to this capital N. So after this capital N onward, all xn will be strictly less than L minus epsilon. By the way, I am constructing this to show that xn lies in the interval L minus epsilon to comma L plus epsilon for all n greater than or equal to some natural number. So in fact, this is that required natural number that would work. So we have shown that therefore xn is strictly greater than L minus epsilon for all n greater than or equal to n. So only thing we need to show that this L plus epsilon is less than xn. Xn is less than L plus epsilon. Now since you know that L is the upper bound, L plus epsilon is also an upper bound, right? Because it's a number which is greater than L plus epsilon, and that's why all xn has to be less than or equal to this L plus epsilon. Okay, so since L is an upper bound, or in fact we are not using the fact that it is supremum, xn has to be less than or equal to L. Okay, and you know that this epsilon is a strictly positive quantity, therefore this L has to be strictly less than L plus epsilon, because you are adding a positive quantity to this L. So we have this, but this is true for all n, there is no restriction. Okay, so therefore we have, okay, I'll mark this as 2. So we have xn is strictly less than L plus epsilon. In fact, this is true for all n belongs to n, and this is true for all n greater than or equal to n. So if I choose this as the natural number, definitely this is true for you. Give me any n, this inequality will always hold. So even if you take small n to be equal to, in particular case, to be capital N, then x capital N is also less than L plus epsilon, x capital N plus 1 is also less than L plus epsilon. So in fact even this is true for all n greater than or equal to n. So therefore for all n greater than or equal to n, we have both this hold. So xn is strictly less than L plus epsilon, and xn is strictly greater than L minus epsilon. This is from, okay, by the way, this should be 3. This is from 2 and 3. So what does it says? That is xn belongs to the interval L minus epsilon comma L plus epsilon, which is same as saying that is mod of xn minus L is strictly less than epsilon. So what we have shown is that for all n greater than or equal to this capital N, the distance between xn and L is strictly less than epsilon. So that's enough to say that the given sequence converges to L. So therefore we say that xn converges to L. So in this theorem we have shown that any increasing sequence which is bounded above converges, and in fact it converges to the least upper bound of the range of the sequence, or the image set of the sequence. Now the only drawback of this theorem is that it do not provide you the accurate limit of the sequence, but through the proof we have seen that the least upper bound of the image set of the sequence in this case behaves as the limit of the sequence. Okay, now a very analogous statement one can frame for the decreasing sequence would be this. So I'll call this as theorem 2.10, which says that let xn be a decreasing sequence. So once it is a decreasing sequence, we know that it is bounded above. So then it is convergent if and only if it is bounded. Okay, or in other words, when I say a decreasing sequence bounded, it's always bounded above, so it is bounded below. So the proof of this I would leave it as an exercise. One can prove it in a similar way, the way I have proved for the increasing sequence. In this case, you are going to use the fact again LUB property, but for the GLB property. Instead of LUB, you will be using GLB property, which is in fact an equivalent statement for an LUB property. You will have a range of the image set of the sequence will be bounded below, and it's going to be non-empty, so therefore it should have a infimum. Okay, and you claim that the given sequence converges to the infimum of that particular sequence using the definition of infimum. So I leave the proof as an exercise. So combining these two combining these two theorem, we have a result. One can conclude that this is called as the monotone convergent theorem, and both this theorem are a part of monotone convergence theorem. So a given sequence xn, given xn of real number which is monotone is convergent if and only if it is bounded. And the proof for this is the sum of both the proof which we have proved above. Okay. There's a notation we use here. If the given sequence is increasing, then we use a notation, and if it converges to say some point x, we use this notation xn. This is the first one, xn, the arrow moving upward x. This stands for xn is increasing and converges to is increasing and converges to x. Similarly, if I have this notation, then this means that xn is decreasing and converges to x. Okay. This theorem plays a crucial role in proving most of the standard sequences convergent. Okay, but the only drawback of this sequence that it doesn't give a limit of a sequence. We need to construct a limit of the sequence through the idea which we have seen in the proof. So thank you for watching this video and have a nice day ahead.